Hi everybody, my name is Stas. Whoever been in the class on probability knows me. Whoever is, for him it's the first time in my class, very nice to meet you. I'm going to be the lecturer of statistical mechanics for this semester. And before we start to actually talk about the material, let me introduce a little bit what is going to happen generally in this class and my perspective of this subject. So the class is going to be in English, as you know. But if you have questions and you're wondering, I cannot really ask this because I have to translate it into English, etc., etc. It's going to take me some time. Ask in Hebrew, I will translate it, and I will answer you in English. So do not hesitate to ask questions, whatever language you're using. I speak Russian, Hebrew, English, and some Estonian, a little bit. All right, now, you studied analytical mechanics, classical mechanics, electrodynamics, and a bunch of other physical classes. And in most of these classes, you've been dealing with one-body problem, two-body problems, but almost no one taught you anything about the three-body problem. Now, why is that? Why nobody really taught you anything about the three-body problem? The answer is that in most cases, the three-body problem is unsolvable. So we have very simple explanation over here. So here we have three masses that attract each other using gravitational forces, right? And we see those complex trajectories that are created. We start three-body problem with elastic forces. The trajectories are completely different. Moreover, there is another problem over here that's, again, some gravitational forces. The point of this slide is to tell you, well, three-body problem is already extremely complex subject. And around the end of the 19th century, this guy, he was a mathematician, Henri Poincaré, he proved that the three-body problem leads to something that we call now chaos. It's basically unpredictability of the trajectories or of the behavior of the system. What do I mean by unpredictability? So if you take a particle and we'll calculate its trajectory from some specific position, right? So this is a trajectory you can think about as a trajectory of a particle, or a trajectory in some phase space of the system. We shift the initial conditions a little bit by some infinitesimal amount, and the trajectory is going to behave completely different. The distance between the trajectories is going to diverge extremely fast. So this is what we call chaos. You slightly interfere with the initial conditions of the system, and the behavior is going to be completely different, right? So if you think about two masses connected to a spring, well, you shift one mass a little bit to the right, you shift the other mass a little bit to the left, nothing extremely interesting happens. It's still two masses connected by a spring. But if you connect to this guy, to this system, another mass, and you shift the initial conditions a little bit, the behavior can be completely different. So this is what we call chaos, and this is the complexity of the system. Now, so the three-body is already unsolvable. So this is why in most classes you treated one particle, two particles. Sometimes you said, no, Stas, we actually did something that's called rigid mass in mechanics, and we had plates in electrodynamics, and we had wires. There's a lot of particles over there, but eventually all those systems were either one single body, and you acted as if it is one single particle with some specific properties. The same goes for electrodynamics. Why, again, three-body is an unsolvable problem. What we are going to do in our class, we're going to go and treat systems that are not 2-body, 3-body, 4-body, 10 bodies that are completely unsolvable, but we are going to treat systems that have huge number of particles. So this is like 10 to the 23. Most of the system that you look upon have huge number of particles inside. And this is some sort of a miracle, you can say, or a dilemma. How come we cannot solve 3-body problem, 4-body problem, or 10-body problem? Well, we can maybe push it into some computer simulation and simulate the behavior, but we cannot solve it and obtain predictions. And what I'm going to show you in our class, that for big systems, large systems, where there are huge number of particles, you actually can do it. So there is some sort of transition. Small number of particles, exact solutions, no. Big number of particles, exact solution, also no. But probabilistic solutions, yes indeed. So if you look on some systems, so for example, if you look on a current, okay, in a very simple electric circuit. So, well, yeah, you took a class about it and you know what is the voltage, what is the current, how many watts you need in order to shine this bulb over here. But you look inside the system, right, there is a bunch of stuff going on. Okay? So there are electrons, there are ions. Those ions are deflected, reflected by those ions. Something happens, and eventually, well, you have a current, and you have very simple laws to explain this current. But this is, nobody really taught you that, but this is some sort of a probabilistic idea. Why? Because from this current, you cannot say what happens to one single electron inside. But actually, the average behavior, the probabilities, the probability density functions, some correlations, all of this can be obtained only due to the fact that we actually looking on huge number of particles. This is statistical mechanics. The treatment of everything becomes statistics. I can compute averages, I can compute probabilities, but only in this extremely large limit of large number of particles. Nothing in between, absolutely nothing. It's very predictable. Okay? I can now operate in the language of probabilities. I can operate in the language of averages, but I cannot describe to you anything about the deterministic world. So, deterministic prescription in our class at least, and in the class of quantum mechanics, and in almost any modern aspect of physics, is basically dead. You cannot describe complex systems using determinism. So in the words of Ayn Rand, you can ignore reality, but you cannot ignore the consequences of ignoring. So in order to do something practical, in order to understand how nature works, I have to forget about determinism. Why? Well, because I cannot solve this. I cannot predict anything. I cannot reason. Well, I can stay in this realm. Let's solve something about one particle, two particles. Let's develop Lagrangian mechanics. But solvability, if there is such a word in English, is something that I cannot do for real systems. And I have to go into this probabilistic thinking. So the language in statistical physics is going to be, although it's sometimes hidden, I will tell you what is the energy of the system. But it's actually going to be what is the average energy of the system. I'm going to say, okay, well, what's the state of the system? And the question will be, what is the probability of a specific state? Everything is going to go around probability. Averages, law of large numbers, central limit theorem. Okay? So sometimes we won't mention it, but it will always be by the background of this class. So all the results, why they are applicable, why you can actually say something about any system, and you cannot say something about very small system, is because of the mathematical theory that gives you the law of large numbers, if you remember. What is this? I will remind you later. And what is the central limit theorem? You add some stuff, you add more stuff, and a Gaussian appears. How? Why? Well, it's a theorem, we can prove it. There are limitations to it, but it's always applicable for large systems where they are not, the interactions are not too strong. Now, we usually think about, when we talk about simple systems, how it applies to nature. Right? Now, this class tries to show you that even for very complex systems, okay, where there is strong interactions, where there are sometimes physics is not really clear, but this probabilistic thinking of statistical mechanics actually works. And because it's based on probability, and those probability laws are not too complex, the only thing that they need is a bunch of different stuff and some sort of interactions, okay, they're applicable to a very wide range of systems. Okay, so superconductivity, levitations, phase transitions. Okay, if you look on the kettle and those bubbles of water that appear from nowhere, but actually from the bottom of your kettle, explained by those statistical laws, active motion and swarming of birds, it's the same idea or the same appearance of those bubbles of birds and appearance of bubbles of water. The physical description is very, very, very similar. Jamming, okay, I hope your transit to Bar-Ilan was very smooth today. For some people it's not, but again, the laws of physics, you can describe those jamming transition and trafficking problems, etc., etc., etc. You can say, Stas, they are very different. You have electrons or Cooper pairs over here, ions and water molecules over there, birds and people, and at some point it doesn't matter. Right? It doesn't really matter on who I'm looking. So it can be a person, it can be a bird, it can be an electron. So I need to describe the behavior of many of those guys. And like in central limit theorem, when I add up different stochastic variables, and at some point I only say, well, the only thing that I care about is the mean and the variance, right? And I add them up, and the Gaussian miraculously appears. The same over here. I just need some properties, not a lot of them. I don't really need to understand what this person in this car ate this morning for breakfast. It's irrelevant. There are some very small number of parameters that are relevant for this probabilistic description, and therefore the whole description of everything, very, very, very different systems, is going to be very similar. Now, this is very nice. Yes, jamming and levitations, Cooper pairs, etc., etc. But in this class, we're going to talk about dead stuff. Okay. So not dead people or not dead molecules, but usually we're going to talk about systems that reach equilibrium. I will describe explicitly what I mean by equilibrium, but basically it means that nothing flows, nothing changes. Okay, so life is in some sort of a motion, and we are going to talk about systems that are not moving, nothing inside them moving probabilistically. There are some fluctuations, and this is going to be the focus of our class. So no dynamics, you can say, well, it's some sort of like statics, not exactly. So we are going to talk about equilibrium, and anything that is in equilibrium, it's in some sense, it's already dead. There also are two grays over here. Doesn't matter. I wanted to tell you a story, but we don't really have a lot of time to tell you a story about grays and dead people. A funny other story that takes me to the next slide is this introduction on statistical physics written by David Gottslich, and it says the following. Ludwig Boltzmann, who spent much of his life studying statistical mechanics, died in 1906 by his own. Paul Herrenfest, he was one of his students, carrying on the work, died similarly, again, suicide, in 1933. Now it is our turn to study statistical mechanics. So it's not really funny, but sometimes it is. But it's indeed a difficult subject. It's really a difficult subject, and this is why you see those kinds of distributions of final grades in this class. Okay. Now, if you remember, this is a PDF, probability density. Oh, this is a histogram of the distribution from last year. And as you see, there are two groups of people. So first of all, it's hard for everybody. For every student, and when I was a student, it also was hard for me to accumulate this new material. Now, also, specifically in this class, at least what happened at the last 2 years, because of, well, whatever we have in our crazy country, and also because everything is recorded, there is some sort of assumption from students that, well, I can binge everything at the end of the semester. And it doesn't work like that. It simply does not. Why? I don't really know why, but this is a law of nature for this class. Okay? When you try to binge everything, you usually will go somewhere in this group. Okay? Now, due to this 11% of homework and 22% of quiz, you can go from around 40, 42, it's enough to get you from here to a passing grade, okay? If this is your goal. But still, even to go to the 40, it's hard. You see the peak is around 32, okay? So the peak of this is around 32 for an exam where there are 3 questions and there are 33 points for each of them. So I urge you, come to classes, do the homework. Do the homework yourself, do the homework with your friends. Study for as long as the semester goes. Do not try to understand everything at the end. It won't work. Usually it does not work. And that's it. So if you have any questions about the technical aspects of this class, about this statistical mechanics that I taught you or told you, please ask now. Questions, suggestions, remarks? Nothing. Great. Okay, so now we are going to, I hope I haven't discouraged you with this distribution, and I hope that this year it will be pushed towards somewhere over here. We'll have to see. Okay, so the question is the Bohan Magen. So the technical term Magen means that if you do the quiz or you do not do the quiz, it only affects if it's higher than your final grade. And the answer is yes. Okay? So Bohan Magen means if you don't really want to do the quiz, you don't have to. Okay? But in most cases, the grade of the quiz was higher than the final exam. It's for your benefit to do the quiz.
Stas, what about the homework?
Homework is 11%. You have to submit the homework each week, no exceptions. Unless, you are a reservist or you have a funeral this week.
They are not Magen?
No. No. Other questions? No. Cheer up, it's going to be funny. We start with the first law of thermodynamics. So the first part of this lectures, probably you already heard and seen in the class of Bina, but I will describe the same thermodynamical laws in slightly different fashion. And eventually I want to describe to you a technique that's called Legendre transforms and connections between different thermodynamical potentials. So although you can say, well, I heard this, please bear with me. So the first law of thermodynamics. So what is this first law of thermodynamics? We have to talk about energy. Energy. It's the internal energy of the system. We will describe exactly what it is. And when I tell you energy, I'm saying that this is the average energy of my system. Okay? What I mean is I have a box, and inside this box I have huge number of particles. Think about of the gas. Okay? I have huge number of particles. How many? 10 to the power 23, around the Avogadro number of particles. Huge, huge number of particles. When I'm saying that there is a specific energy of the system, I assume that there are some fluctuations this particle can get some larger energy, this particle can get some lower energy, etc., 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 etc. On average, the internal energy of the system is my E, or sometimes I will call it U. Okay. This is the internal energy of the system. I have assumptions when I'm talking about the energy of the system. Those assumptions are going to be encoded in whole class. Energy is extensive. What do I mean by extensivity? Extensivity, it's a linear dependence on the size of the system. That's it. So if I have two systems divided by some wall, and the energy of the left-hand side is E1, the energy, internal energy, of the right-hand side is E2, I'm saying that the total energy E is E1 plus E2. Okay. Very simple, very nice, but this is an assumption. When I wrote this assumption that energy is extensive, I neglected something. What do I neglected? What do you think? What happens over here? Okay. So there is a boundary, right? I have two systems. I connected them. Think about it. I connected those two systems. There is a boundary. Inside this boundary, there can be interactions between whatever sits on the left-hand side and with whatever sits on the right-hand side. So there is some sort of interactions between the two systems. And when I'm saying that the total energy is just the internal energy E1 plus the internal energy E2, I have neglected this interaction energy. The energy of the boundary is completely neglected. And that's why can you do that? It's an assumption. So first of all, we're going to have a lot of assumptions in this class. And second of all, well, we have this huge number of particles, right? So look on this guy. So there is 10 to the power 23 of particles sitting over here. There is 10 to the power 23 particles of sitting over on the right hand side. How many particles are sitting on the boundary? My assumption is that the number of particles that sit on the boundary and interact with each other, it's comparably small to the number of particles that are sitting on the left-hand side and on the right-hand side. Okay. This is a strong assumption, but for most systems, this extensivity works extremely well. What do you think are systems where this extensivity won't work? So there are, yes? Small number of particles. Excellent. If I'm having a system, okay, that I have one particle and I have another particle, and I connect them, and this connection makes some sort of a spring connection, I cannot neglect those interactions due to the spring now, right? I simply can't, otherwise I cannot solve the system. So it doesn't work when we have small number of particles because the assumption uses this huge number of particles in each system. So this is system number where it won't work. Small systems, we won't talk about them. There is a whole branch of statistical physics that called mesoscopic physics that deals with systems with small number of particles. Another assumption is what? Yes?
Maybe a larger border.
Larger border.
If E1 is enclosed inside E2, and in the middle of it, so you still have a border and a lot more interactions.
Great.
So maybe
Great. So I will extend your claim and I will say, what if the only thing that we are looking on, so let's assume that we have shallow water. So we have small number of water. We have water here on the bottom of this cup. And there is vapor. Okay? And I have some boundary between the water and the vapor. Now, in this situation, although that I have many particles in this water, I also have many particles, or comparable number of particles, on the boundary. Okay? So, in this situation, I cannot simply say, well, the total energy is the energy of the vapor and the energy of whatever shallow amount of water that I have in the cup. I also need to consider the tension energy of the boundary. It's very, very important. Why again? Because the number of particles on the boundary is comparable to the number of particles, although there are a huge number of particles, is comparable to the number of particles inside the system itself. And there is third example, yes?
When individual particles can reach an equilibrium that changes the fundamental properties of the two particles. For example, say positive ions and negative ions.
No. So we haven't spoke about equilibrium yet, but maybe you're trying to say the following thing. When I'm looking over this system and I'm saying, well, extensivity, I'm also saying the following thing. So whatever particles that I have inside on the left-hand side and whatever particles that I have on the right-hand side, they are interacting mostly with themselves, right? So this particle have a radius of interactions of this size, and this particle over here have a radius of interactions of that size, and it goes for every other particle that I have inside the system. But what if this particle actually interacts strongly and non-negligibly with this particle on the right-hand side? What I'm saying is, what if the radius of interaction of my particles is actually big? In such situations, when the radius of interactions is very, 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 very large, okay, I don't have a restricted boundary. All the particles have to do something. On the right-hand side, they interact with all the particles on the left-hand side, etc., etc. There is basically almost no boundary. In such situations, again, the energy is not extensive. So, what do you know, or what systems do you know that they have huge radius of interactions? Electromagnetic interaction. Okay, so it goes as 1 over r squared. Gravitational interaction, it goes over 1 over r squared. Those are very extensive, very large interactions, and therefore for such systems, this assumption won't work. Okay. Now you can say, Stas, but wait a minute. We are trying to speak about regular matter, and all the basic interactions inside any solids, or soft matter, or liquid, are electromagnetic interactions. Stuff like van der Waals, etc., etc. They are based on electromagnetic interactions. Okay? And you're saying that for those electromagnetic interactions, the radius of interaction is extremely large, so it's not applicable. So what is your theory is applicable to? And the answer is, well, there's a big difference between two particles, okay, where there is nothing outside of them, and they are indeed interacting with each other according to the Coulomb law, which goes as 1 over r squared. But if there are other particles, there is some effect called screening. Okay? So if I put two particles, one next to each other, the only thing that matters is 1 over r squared. And this is r. But if I put a bunch of other particles around them, there is an electromagnetic screening effect, and the interaction goes as e to the minus r divided by some r0. You can say, Stas, what does it doesn't matter, power law, exponential, it is matter. It's extremely important and extremely different states of interactions exponential interactions, which are most of the effective interactions that we have around us, and those pure parallel interactions. If everything was just defined by those pure parallel interactions, we'll be doomed. Statistical mechanics would be dead. But luckily for us, almost everything, due to the presence of huge number of particles around us, the interactions, effective interactions, have this form. Therefore, they're going to be finite radius of interactions, and this extensivity will survive. So we're assuming we have energy. We're assuming that the energy is always extensive. For anything that we're going to do in this class, energy is always extensive. So if I'm doing something and the energy is not extensive, I'm doing it wrong. We forgot something, we haven't assumed something, we have done something terribly wrong, and there are a bunch of questions in the exam when I give you an equation and I say, is this a correct equation? And you have to say, well, no, it's not extensive. Extensivity of the energy is very important. Okay, so if we have an energy, we have E1, we have E2, and we have E3, and we have E4, the total energy of the system is going to be E1 plus E2 plus E3 plus E4. Okay, so this is energy. The first law of thermodynamics tells us something of how this energy is changing, or how this energy is conserved. So we just write it down. If our energy is somehow changing, there are two ways of how it's going to be modified. Either you're going to heat the system somehow, okay? So this is the amount of heat that got into the system. Plus the work or the that was performed on the system. Now, what is exactly this heat? What exactly is this heat? So this heat, it's very simple. You take something, you burn it, and due to this burning process, energy is transferred from one substance to another. So let's assume that I put a fire. How do I make a fire? I burn coal, I burn food, I burn something. On top of this fire, I have water. So the fire is burning, the water starts to boil, there is a transformation. Transformation is that part of the water is transformed into vapor. The vapor goes up, and here I have a propeller that starts to rotate. Due to the rotation of this propeller, I'm creating electric energy. I have light in my house, I have air conditioning, and I can actually speak, and my lecture is recorded. The electricity company is actually burning something. It's burning either coal or it's burning gas. The sun electricity is also coming from burning something, burning of helium. Far, far, far away from us. But due to this flow of heat, there is some work that is produced. So this first part is sometimes uncontrolled flow of heat inside the system. What is this work and how exactly we define it, I will describe to you on the next lecture. So Tuesday you have a happy hour inside of my lecture, as far as I understand. So I'm going to meet you next week on Monday. That's it. Thank you.
Thank you very much.
Thank you. Bye.
זה יתאבד. הפסקה שעה.